Everyone, my name is Amir Mohammad Naseri, and I'm going to present our paper with the title of An Observer-Based Key Agreement Scheme for Remotely Controlled Mobile Robots. Other authors of paper are Dr. Walter Lucia and Dr. Amir Youssef from Concordia University. In this slide, you can see the content of this presentation. As an introduction, main motivations of this work can be summarized into the following items. First of all, to guarantee any component of the CIA triad, a secret must be shared between the plant and the controller. Also, in popular CPS security solution, we need a pre-shared secret. It can be a seed, it can be a pseudo-random number, or anything else. The literature lack of control theoretic key establishment protocols leveraging the physical dynamic of the control system can be considered as the third item. And we are also using a wheeled mobile robot as our case study, CPS case study, because the potential application of mobile robot in network control system including safety critical systems are expanding, and such development raised the concern about the security and privacy of the information in these systems. To review the literature, traditionally a key agreement was achieved through the use of symmetric or public key cryptographic protocols. Also, we have key establishment solutions based on the concept of wiretap channel. In these schemes, we are leveraging the role of noise in the communication channels. Beyond that, we have different key agreement protocols have been developed using the Wiener channel idea. The first protocol, leveraging physical properties of control system in CPS, can be found in this paper, and after that, in these two papers, control theoretic approaches have been proposed to design key agreement schemes leveraging the asymmetry in the CPS model knowledge available to the defender and the adversary. So, our contributions can be summarized in these three items. First of all, we extended the key agreement protocol proposed in this paper to deal with nonlinear plant dynamics. Also, we tailored the solution to deal with nonlinear dynamic of wheeled mobile robots, which is our case study, and we verified the proposed solution on a remotely maneuver Capera 4 robot as an example of mobile robots. In this slide, you can see the discretized model of a differential drive robot. Basically, we can model this robot with the following parameters. In this model, T is the sampling time of the system, R is the radius of the wheels of the robot, D is the length of the axle of the robot, W and V are the covariance matrices of the measurement and process noise, and H is a nonlinear output equation describing the available sensor measurements. In this paper, we consider a passive adversary capable of eavesdropping the control input and sensor measurements transmitted between the robot and the network controller. Also, the adversary is aware that the robot is a differential drive robot. And if we indicate the model of the adversary from the robot with MA, this model is not as accurate as the actual model of the robot because the adversary doesn't know the exact value of some of the parameters. So, our objective is, without resorting to traditional cryptographic scheme, design a key agreement protocol between the robot and the network controller such that the key which is recovered by the controller should be the same as the robot key, but the key, which is recovered by the Eve, should be different. We also made the following assumption in this paper. First, there exists an unknown input observer for both controller and attacker, capable of simultaneously estimating the control input and state of the robot. Second, the robot is equipped with a tracking controller that provides a proper control input to the robot. In this slide, I'm going to explain our proposed protocol in this paper. The proposed key agreement protocol can be summarized into the following items. First of all, the controller computes the control input UK, and then by using the control input, it generates two perturbated control input. We call them U0 and U1. Controller can compute U0 and U1 by adding and subtracting a constant value to the original control input. After that, the controller will send both control input to the robot, and the robot select one of them randomly based on a random generated bit at each time step. After selecting the control input, the robot sends the selected control input to the actuators. After that, a controller will receive a sensor measurement YK at each time step and run the unknown input observer. The controller doesn't know the exact value of the selected bit, so it just can have an estimation of the selected bit by using the output of the unknown input observer. It should be noted that the adversary can also run the same unknown input observer with the model it has. However, given the model discrepancy, the covariance of the unknown input estimation error for the attacker is expected to be larger of the one obtained by the controller. Consequently, for a proper choice of delta, the constant value, it is expected that the controller and robot can share the same key, but the key which is recovered by the attacker is expected to be different. So the proposed protocol, the key agreement protocol in the previous slide, is not robust against possible model mismatch and process and measurement noises. So to enhance the robustness, we can use an error correction code mechanism and a feedback acknowledgement signal in our protocol. In this slide, I'm going to explain our experimental result with using a Capera-4 robot. Basically, in our experiment, the robot is supposed to follow the trajectory while the controller is implemented on a remote computer, and the computer and the robot are communicating through the Bluetooth protocol. So the state of the robot has been estimated via odometric calculation. In our experiment, we use the unknown input estimator proposed in this paper. For the error correction code mechanism, we are using blocks of the length of 3, so we have a redundancy of 3 for each bit. And for the policy to accept a block, we are using consensus policy, which means that we accept a block if all the bits are in the block are the same. Next, the protocol is tested for the bias value in this range, and it's applied on the linear velocity of the robot. And we did the experiment for each delta V 10 times with different random generated keys. So as you can see in the obtained results, On the left hand side we have the percentage of bits accepted in the red curve, and we have the correctly decoded bits in the blue curve. For different value of delta V, our bias in this range, and as you can see, for the value of delta V equal to 0.035, it's the first value in which we have the 100% correct decoding. And on the right hand side you can see the average tracking error for different values of delta V. In this slide I'm going to show you a demo of the experiment that we did with the Capera 4 robot. On the left hand side you can see the performance of the controller without key agreement protocol, which means delta V is equal to 0. And on the right hand side you can see the performance of the controller with the value of delta V equal to 0.035. So as you can see in this video, in this demo, we are comparing the performance of the robot in following the square trajectory with and without this queue agreement protocol. Also, at the same time, you can see the number of accepted code words and the number of bits correctly decoded on the right hand side, and also the percentage. As you can see, adding this key agreement protocol does not affect the performance of the controller in following the trajectory. So, as the conclusion of this presentation, a key agreement protocol has been developed for a remotely controlled mobile robot without resorting to the traditional cryptographic approaches. The asymmetries between the controller's and adversary's knowledge about the mobile robot model is leveraged to develop the key agreement scheme. The protocol is developed based on a nonlinear unknown input observer and an error correction code mechanism. And also, the proposed solution has been tested and validated by using a Capera 4 robot. The experimental results confirm the effectiveness of the proposed scheme. Thank you for your attention, and these are some of the references we use in this paper.